Hey everybody, so we're going to do another example using lines and planes. So this problem is we want to find the line of intersection between two planes. Okay, so that's what we're going to be working on. Let's start though by just looking at, let's just try to get a good picture of what's exactly happening here, because it might not be exactly clear if you're not as familiar with this stuff. So here I've got a graph going of the two planes, okay? So the blue one is x plus y plus z equals 1, and the orange one is x minus 2y plus 3z equals 1. So we can see more or less there that the intersection between these two things is a plane, right? You can imagine pages in a book, right? If you hold a book open, right, the spine between them, there's a line that we can think of there. Let's make that a little more defined. So I've put in what will end up being the line that we find, right? So there's that dotted line is what it looks like. And let's do this. Let's pull the axes out now. We kind of already know where they are. Now we can just sort of see, now I can just see what's happening here. So let's put in a couple of other things so we understand, get a little strategy here. So this line, whenever we find it, is going to have a vector that tells us its direction, right? So I've put in this vector v here. And we also have the vectors, the normal vectors for our two planes, okay? So we can see this orange one is perpendicular to the orange plane. The blue one we can see maybe here is perpendicular to the blue plane. So those are the normal vectors, and I read those straight off of the equations, right? So for instance, equation 1 right here, right? We can just read the coefficients of x, y, and z to see that, I guess I called that one n, is just 1, 1, 1. Right? And then the other one, I'm reading off the coefficients of equation 2 here. M is going to be, that was 1, minus 2, 3, right? So that's where we can find those normal vectors from the equation. So I've put those out there. I just put them on an arbitrary point in each plane so we can kind of see what they look like. But I want to do something a little different with them. Let me now, this is where it comes in handy to be able to think of these vectors as geometric objects that we can move around and play with. So I'm going to move the vectors, all of these vectors that I have out there right now, so that their initial points are at the same place. So let me just get them into a convenient spot. So I moved one. Let's see. Let's move this one. Oops. All right, so now the orange and the blue are in the same place, and we might start to notice something about them. Let's put that direction vector out there in the same place as those two. Put its initial point in the same place. All right, so now the direction, so what we're looking at is the black is the direction vector of the line, and the blue and the orange are the normal vectors for our two planes. Let's even pull the planes out of this thing. Oops, I turned off the wrong thing. What do we notice is that the direction vector is perpendicular to both of them. Okay, so here's how to think about that. The direction vector has to lie along that line. That line's in the intersection of both planes. In other words, every point in that line is in both planes. So if I have a vector along that line, it has to lie in both planes. Well, these are the normal vectors. The normal vector for each plane has to be perpendicular to every vector in the plane. And so since this vector is in both of them, it's perpendicular to both. So this gives us an idea for a strategy here to find the direction vector for the plane. We can look at the cross product of the two normal vectors. Okay, so let's go back to a little more space and work this problem out now that we have a little bit of a strategy. All right, so let me move this down. Okay, so what are we going to do? Well, let's just write out what we have. We had n was equal to 1, 1, 1. M was equal to 1, -2, 3. These are the normal vectors. N is the normal vector for this plane. M is the normal vector for this plane. And what we want is the direction vector of our line is going to be the cross product of these two. Okay? I'm going to call it V. So we take the cross product, and I get, so the first one, we take 1 times 3 from up here, minus 1 times -2, that gives me a 5. Then I take 1 minus 3, gives me a -2. Then I take -2 minus 1, gives me a -3. Okay, so I'm just computing a cross product there. Okay, so remember, sorry, let me pull this together as well. Our equation, right? We're going to need R0 plus TV. Sorry, I should have said this first. And remember what V is. V is the direction vector. We've already got that. R0 is just got to be a point on the line. In this case, that means a point on both equations, satisfying both equations. Okay, so we need to find a triple, 3 numbers that satisfy both of these plane equations. Okay, so that's our next job here. And the little insight we're going to use is this. Look at our direction vector. All 3 of the components are non-zero. That means whatever the vector R, right, is changing in all 3 components, right? So in other words, its X, Y, and Z components will eventually each be equal to every single real number, right? No matter what R0 is, if I add to it T times V, let's just think about the X component for a second. I'm starting with a number and I'm adding 5 times T to it. I can get to any number I want, right? X0 plus T times 5. I'm saying this can be equal to any number. If we know what X0 was, so let's say this is equal to 2. 2 plus T times 5, give me any number like 19, and I can find a T that makes this true. Give me a number like 190, I can find a T that makes this true. Make that negative, I can find a T that makes this true, right? We just solve this equation. More generally, X0 plus T times 5 equals some number, let's call it N. We just need to find the T that makes it true. Well, that's just going to be N minus X0 divided by 5, right? Doing that algebra. So again, once we know a point, if given any point on that line, we can get to any other X value through this equation. So the big takeaway from this is, eventually, all of these coordinates will be 0 at some point. Not at the same time, right? I want to be clear about this. This is not at the same time, okay? And I can say that about all 3 of them because all 3 of the vector components are non-zero, because V is telling us how those components change, right? How we move along this line. For instance, that means at some point on the line, the Z coordinate is equal to 0. Okay. Now I chose Z arbitrarily, mostly because the Z part of the equation is the hardest one. It's got the biggest coefficient. It doesn't really matter which one you choose because we've got all 3 non-zero. But in general, any vector, direction vector, for any of the non-zero components, we know that that component will have a coordinate on the line equal to any real number. Okay, and we're taking advantage of that. So here's how we use that. Remember, we wanted to find a point that satisfies these 2 equations. right? And maybe you could guess and check a point using, you could guess and check because these are relatively simple. But if these were things like 2.795, it would be a lot harder to guess and check if they all had weird coefficients. So let's pretend we're not guessing and checking and come up with a strategy. And this is our strategy, knowing that at least one of the points on the line, which is also a point on both planes, satisfies both of these, has a z-coordinate of 0. At that point, it must be true that x plus y equals 1 and x minus 2y equals 1 because the z components are 0. So that's our little trick to solve this equation without having to just guess and check. Now I've got two equations, two unknowns. I'll use, this looks pretty easy to use substitution. X equals 2y plus 1, so I can bring that over to this equation. 2y plus 1 plus y equals 1. Oh, sorry, I thought I got something wrong, but I see what's happening. Which means 3y equals 0 or y equals 0. Which means x equals 0 plus 1 or x equals 0. So that means we already knew z equals 0. The point in question has the coordinates. Sorry, this is x equals 1. 1, 0, 0. And that gives us our r naught. So r naught is going to be equal to 1, 0, 0, which means the equation of this line is r is equal to 1, 0, 0 plus t times 5 minus 2 minus 3, or 1 plus 5t minus 2t minus 3t. Okay, and there's our nice vector equation of the line. Keep in mind, this is completely not unique. There are many equations, vector equations, that would be indicating the exact same line. For instance, I could have made the same argument about the x-coordinate, and we could have started with the x-coordinate as 0 and gotten a different point on this line. I could have done guess and check and gotten a different point. I didn't have to use the value 0 either. I just did because it's easy. If I said, I could make the same argument and say the z-coordinate at some point has to be 1,000 and put 1,000 in here and solve these equations to get another point. So there's nothing unique about this equation. The same thing with v. I could have done m cross n. Then I know I would have gotten this, but negative. I could take a scaled version of this. All of those things would work. I just did what seemed like the path of least resistance and got this equation of the line. What should be true for any solution, it should have this, the direction vector should be a scalar multiple of v, right? They have to be parallel, otherwise they're not, otherwise one of them's wrong, if not both of them. And the point has to be in the intersection of both planes, meaning satisfying both of these equations, which ours certainly does. All right, let's take a look at this on the other screen, with a nice graph. So let me get rid of all the pictures. So let's bring some of the stuff back I had removed before. So remember, we started with these two equations. They're normal vectors, which I've pulled them off of their respective planes to look at them, are now perpendicular to v that we got by taking their cross product. And so I made a line with that direction vector. You can see it down at the bottom on the left-hand side here. They use lambda instead of t for their parameter. That doesn't matter, and the point 1, 0, 0. So they're looking at the same, that's the exact equation that I came up with. Okay, that is it. Thanks, everybody. I will see you next time.